Melos todos. Menos uno, dos, tres. Okay, I think we are live. So welcome everyone to the Latin American webinars on physics. I'm Nicolás Bernal from Universidad Antonio Nariño in Bogotá, Colombia, and I will be your host today. So we're super happy because we have Yuber Perez-Gonzalez here today. We'll talk about neutrinos from Primordial Black Holes and opera in two acts. So Yuber got his PhD at Universidad de Sao Paulo, USP, in Brazil. And now he's doing a postdoc at Fermilab at Northwest University in USA. And if I understood correctly, he's about to move to Durham, right?
Yes.
At some point
yes.
in October, I think. So we're super happy to have him here. So remember that you can ask questions via the YouTube channel, the chat, and okay, Yuber, the floor is all yours.
Okay. First of all, thanks very much for the opportunity to talk here. Let me start sharing my slides. Okay, yes, Nicolas was saying, I will talk to you about these works that I've done about neutrinos and primordial black holes. So I like classical music, and I try to write these slides like in a way that is like an opera, and you will see why there are two different acts. So every opera starts with an overture. So this is basically my introduction. And let me just, I usually like to start my talks showing these very nice plots, which shows many of the sources of neutrinos that we know that are in nature, and some neutrinos that are man-made. Like we have, for instance, solar neutrinos, neutrinos from the atmosphere, neutrinos from the AGNs, from the Earth, and man-made neutrinos like reactor antineutrinos. Most of these neutrinos have been measured, like as I was saying, solar, terrestrial, but others haven't been measured yet, like the relic neutrinos from the Big Bang. And from studying these neutrinos, we have learned a lot of things. Like we know that neutrinos have masses, and we have seen this because we have measured the neutrino oscillation phenomena. And this is more or less the current status of what we know about neutrino masses and mixings. These are the last results done from this group that basically they do a global fit from the current data. And as you can see here, we know that basically the data tells us that there are basically three different mixing angles. And this is basically the delta chi-square as function from the different mixing parameters here. We know that there are two different non-zero parameters, mixing angles, and two non-zero quadratic mass differences. One is called solar mass difference, and the other is atmospheric, because these were measured the first time in these types of neutrinos. So other thing that we don't know yet if neutrinos have is what is the value of the delta CP phase. Current values indicate that you can have maximal mixing, but it depends on some unknown parameters. So related to that, there are things that we don't know yet about neutrino mass mixings. The first thing we don't know is that, as you can see here from the probability oscillations that I didn't spoke in detail, this depends on the quadratic mass difference between the mass and gain states. And because of that, we don't know what is the actual value of the neutrino masses. We only know this quadratic difference. And also, we don't know what is the so-called ordering. What we don't know is if, for instance, you can order the neutrinos in such a way that the lightest neutrino is the most composed by electron neutrino. And this is what is called normal ordering. On the other hand, you can also take the lightest neutrino to be the neutrino that is least composed by electron neutrinos. So this is the case when you could have the inverted ordering. So current data, basically, for instance, if you look at specific experiments with accelerated neutrinos, like these two experiments, one called T2K and NOVA, individually, these two experiments prefer this ordering, this normal ordering, while when you do the combination, they prefer the inverted ordering. The reason for this is that the data are a bit, when you do the combination, there is this preference, and it's only because these experiments have measured different expected events. But okay, in any case, this is something we still don't know, and this preference actually is not very significant statistically. So there is more data that is needed in order to understand what is the case for neutrinos. There are things that we don't know about neutrino physics, like for instance, we don't know, as I was mentioning, the value of the delta CP phase. There are some hints, but from looking just at the delta chi square, we see that there is a preference, but it's not significant. And other thing that we don't know about neutrinos is their fundamental nature. And for me, this is a more difficult question to answer, and also more important question to answer. By this, I mean, we don't know if neutrinos are Dirac or Majorana particles. By this, I mean that if we don't know if neutrinos are their own antiparticles or not. There are some ways that you can try to look for this. For instance, you can look for the neutrinoless double bit decay, and has been proven that if you find this type of decay, this will indicate that neutrinos are Majorana particles. On the other hand, you can look for, you can assume that the heavy right-handed neutrinos or heavy neutrinos in general exist. And this, if you study the energy and angle distribution of the decays, you can point out if the heavy neutrino is Dirac or Majorana. But okay, you may ask, well, what is the relation with the lightest neutrino, with the active neutrino that we know? The relation is that in principle, you can always have mixing, and the mixing will always communicate the true nature. So if you find in some sense, what is the nature of these heavy neutrinos, you will know indirectly what is the nature of the active neutrinos. But what is the reason that we don't know yet why if neutrinos are, whether neutrinos are Dirac or Majorana? The reason is that all the effects that differentiate between these two are very, only appear for non-relativistic particles. And in all the experiments that we have with neutrinos, neutrinos are basically ultra-relativistic particles. And so the effects that differentiate are basically negligible. So one idea would be, well, try to look for these non-relativistic neutrinos. We know that in nature, there could be at least one type of non-relativistic neutrinos. And these are the neutrinos that I talked before, that these are the cosmic neutrino background or the relics from the Big Bang. So some people have pointed out that if you are able to detect this cosmic neutrino background, for instance, using the capture by, for instance, you can have a neutrino that interacts with a neutron, producing a positron, a proton, and electron. And if you measure to the energy of this electron, you will be able to tag and say that this is coming from a neutrino from the cosmic neutrino background. And more importantly, you will be able to see if neutrinos are Dirac or Majorana, because in principle, the capture rate of this cosmic neutrino background is twice the value for Majorana compared to Dirac. So in principle, if you are able to measure these neutrinos and you look at the capture rate, you will say if it's twice the value that you expect for Dirac or not. And then you will be able to say, in principle, if neutrinos are Dirac or Majorana. There are some issues related to this simplified view that I just spoke about. And the reason is that we don't know actually what is the flux of these neutrinos at the Earth. So probably we can have large uncertainties, and differentiated, like looking for this value of 2 could be complicated. And also, other thing that we point out some time ago is that in principle, this is only true if you only have standard model interactions. If you have additional interactions, in principle, you can enhance the Dirac capture rate and make it twice, even though neutrinos are Dirac particles. But okay, so we may wonder, well, this is only for the case of this cosmic neutrino background that appears here. And the reason is, and we may wonder, well, are there other mechanisms to produce neutrinos that are not weak decays? And if so, it would be possible to differentiate between Dirac and Majorana. One simple case that we can consider is the emission of neutrinos from primordial black holes. And this will be what I will focus on the remainder of the talk. So what are primordial black holes? So let me just remind you that if a star, for instance, if a initial star had some initial mass bigger than the 3 solar masses, this will form, what I wanted to say is that black holes that are formed from star collapse will only have masses bigger than 3 solar masses. And these what are called astrophysical black holes. So in principle, if you want to have black holes with lower masses than this constraint, you would require higher densities. And these densities would only, in principle, would be present in the early universe. So if you want to have black holes which have masses less than the three solar masses, you can look for in the early universe, and these are the so-called primordial black holes. So there are many ways that you, in principle, can form, can have some initial formation of these black holes, and there are many mechanisms. Like, for instance, you can have some phase transition that can create bubble collisions. That you can have, for instance, other cases that you can have some pressure reduction or collapse of density fluctuations that will lead to formation of black holes in the early universe. But I won't focus much in the formation mechanism. I will assume that you have some initial density of black holes, and then analyze the phenomenological consequences, specifically related to neutrinos. The crucial point is that when the Schwarzschild radius of a primordial black hole is close to the Compton wavelength of some particle, the quantum effects become important. And as Hawking demonstrated, black holes start to evaporate and start to emit particles with a thermal distribution. So let me just remind you briefly about about this black hole evaporation. So since black holes are emitting these particles, they are losing mass over time. And basically, you can estimate what is the rate of emission of the rate of mass loss as function of time. And you just equate this because you know that it's energy conservation. So when a black hole emits one particle, the black hole should lose a equivalent mass to this. So in principle, you can parameterize what is the mass loss rate. And this depends on a very important quantity, that is the black hole temperature. That is for non-rotating black hole is given by this expression. So when we put numbers with basically, when a black hole has a mass of 10 to the 13 gram, it has a temperature of about 1 GeV. So when you study what is the lifetime of a black hole, for instance, it's basically integrating this rate over the time. And you can put, for instance, some initial masses and see what is the lifetime of some given black hole. So if, for instance, you consider a black hole with the initial mass equal to the solar mass, you find that the lifetime of this such black hole would be extremely huge, would be 10 to the 67 years, or many orders of magnitude bigger than the age of the universe. But in principle, you could have some black holes that originated in the early universe and would evaporate now. So this is more or less the landscape of the parameters that we will consider here. Basically, we will have first the fraction of the total energy, the initial energy density, that in the early universe became a density of black holes. And this will be parameterized by this beta prime parameter. Beta is basically the initial density of black holes, so over the total energy density. And beta prime is just related to beta after adding some parameters like the gravitational collapse factor as some dependence on the relativistic degrees of freedom. It's just a reparameterization of this beta. So we can see that depending on the initial mass, that is what we have in the x-axis, the constraints can be different. And there is a crucial value, that is the value I was speaking before. If a black hole had an initial mass of about 10 to the 15 grams, it would have evaporated today. So black holes that had an initial mass smaller than this value would have already evaporated. And depending on when they evaporated, the constraints can be strong or not. For instance, black holes could have evaporated during the BBN era and would change what we observe. So the constraints here are actually very strong because of that. If a black hole evaporates there, you have very strong constraints. Other things that black holes could have evaporated during the SMB formation, and again, we have measured with very precisely this, and thus we can put very strong constraints. If black holes evaporated before BBN, the constraints are much weaker, but I will come back to this later. On the other hand, if black holes had an initial mass bigger than 10 to the 15 gram, they could be still around, and they could be part of the dark matter. So you can translate these constraints on beta prime and consider instead the dark matter fraction that, the fraction of black holes that are the dark matter. So you can see here some recent constraints, and from this you observe that there is still some window that is open in which all the dark matter could be formed of black holes. But again, my purpose is only considering, I will focus more on what's the impact of having the Hawking radiation and specifically the emission of neutrinos from primordial black holes. So in the 70s, when Hawking demonstrated that black holes emit particles, it was noticed that, of course, neutrinos are among the particles that are emitted. And more importantly, there are two different ways to emit neutrinos from a black hole. First, a direct emission, where the black hole directly emits because of Hawking radiation. And second, before that, I just wanted to point out what is the Hawking spectrum, the Hawking rate. And this Hawking rate will depend crucially in the degrees of freedom of the particle that is emitted, and also in the so-called absorption cross-section. That is basically a quantity that tells you that you can have some backscattering, because when these particles are emitted, they propagate in a curved space-time. But okay, there is a second way to produce neutrinos from black holes, from black holes in general. So in principle, a black hole can emit some unstable particle like a quark or a muon, and this muon will decay producing neutrinos. And this is the second, what is called the secondary component. Also, for instance, a quark can be emitted, and this quark can be hadronized and led, for instance, to the formation of a pion, and this pion will decay again, producing neutrinos. So there are some constraints when you look at these two components. But interestingly, when this was noticed, people were not aware that neutrinos are massive particles. So we, in this work, we ask ourselves, well, what is the effect of having neutrinos as massive particles in the emission of from primordial black holes or black holes in general? The first thing that we notice is that the secondary component, since this is coming basically from weak interactions here, because this is coming from the case of particles, is not very affected because of neutrinos, because of the mass of neutrinos. And this is in general what happens in all weak interactions. Nevertheless, the primary component, it can be mainly affected because we need to worry what is the number of degrees of freedom that are emitted, and this will depend on the mass of the neutrinos. So let me just compare between weak interactions, the Hawking effect, to understand what is the difference here. On the first hand, in weak interactions, the interactions that we know, for instance, in the case of a neutron that is decaying, it produces a proton, electron, and an anti-electron neutrino. Interestingly, these type of interactions are mediated by a gauge boson. And when you emit, for instance, a neutrino, you assign the flavor related to the charged lepton that is emitted. So in this case, we are saying that this neutrino has a flavor, electron flavor, because we know that what is emitted is an electron. So in this case, what we say is that weak interactions produce flavor eigenstates. While when we looked at neutrino oscillations, we know that the flavor eigenstates are not fundamental quantities, but they are superposition, what is called the mass eigenstates. On the other hand, the Hawking effect comes from a totally different physics. It comes basically from the fact that a particle definition in a curved space-time depends on the observer. And interestingly, when you study what is the derivation of the Hawking effect, you observe that the fields that are needed when you study this are fields that have well kinematic properties. So we can assume that this has not been proven yet, but it's a good assumption that saying that black holes do not emit flavor eigenstates, but they emit mass eigenstates. The other thing that we notice is that something related to what I was talking before. Since the Hawking evaporation depends on the number of degrees of freedom that you can emit, it will depend on whether neutrinos are Dirac or Majorana particles. For instance, in the case of Majorana particles, you will have the active neutrinos that you know and not more. Possibly you can have very heavy neutrinos that can have some phenomenological consequences, and I will come back to this later. The second option is that neutrinos are Dirac particles. So not only the active neutrinos, but the so-called sterile states, right-handed neutrinos and left-handed antineutrinos can be emitted from the primordial black hole. And this would also have some phenomenological consequences. But before going to that, let me just talk about what is the effect of having Dirac or Majorana neutrinos on the black hole evaporation. So as I was talking before, the black hole, the mass rate depends on what's the number of particles that is emitted. And you can look at what is it's called the black hole, the evaporation function. That is basically, let me just go back quickly. This function here, when you add up over all degrees of freedom. So this function can be reparametrized as in function of the so-called evaporation function. And this will depend on neutrinos are Dirac or Majorana, because it will depend on the number of degrees of freedom that can be emitted. So this parameterization here, the evaporation function, here this light orange line corresponds to the case where neutrinos are massless, while the green dashed line corresponds to the case when Majorana, when neutrinos are Majorana, or the blue dotted is when neutrinos are Dirac. So as we can see here, the main effect in the Dirac case is that since you are having 2 additional degrees of freedom, since black holes can emit these right-handed neutrinos and left-handed antineutrinos, you have an enhancement on this evaporation function. But at some point, since neutrinos are massive, there is a point that, well, black holes stop emitting these neutrinos. And the reason is that, let me go back here, there is a Boltzmann suppression related to the temperature of the black hole. And basically, you can understand this by noticing when the temperature of the black hole is smaller than the mass of the particle, this has a strong exponential suppression or a Boltzmann suppression. So you have less production of these particles because of their masses. So this will depend on the actual value of the masses. But if you assume some values here, you expect that this effect will be when the initial black hole mass is around 10 to the 24 grams. Other thing that we can compare is basically the lifetime of a black hole compared to the case of massless neutrinos. And this ratio is 1 when neutrinos are massless. So you see here that when neutrinos have already evaporated, like the value before 10 to the 15 grams, the effect of having these additional degrees of freedom is basically about 5%. And the reason is that these black holes would have evaporated and emitted all types of particles, and the number of the additional 2 degrees of freedom is not impacting much the lifetime of a black hole. Nevertheless, when the black holes stop emitting some particles, and when that is when the emission of neutrinos become more important, there is a point when the lifetime of a black hole it's half if neutrinos are Dirac in comparison to Majorana or the massless case. But after some point, since as I was saying, the emission of neutrinos can be suppressed because of their masses, this will enhance the lifetime of a black hole because they cannot emit neutrinos and they will emit only photons or gravitons. But the only issue here is that this effect will happen only with black holes that have masses bigger than 10 to the 15 gram. So these black holes would be still around and probably their lifetimes are very large, and this will be something difficult to see experimental. So let me just come back and talk about the difference between Dirac and Majorana neutrinos and just remind you what I was talking just now. So in the case of Dirac neutrinos, I was saying black holes emit these additional degrees of freedom, the right-handed neutrinos and the left-handed antineutrinos. And a very interesting thing is that the emission of these degrees of freedom, it has the same, let's say, probability that it being emitted as the active neutrino. So it's the same probability to emit an active left-handed neutrino to emit a right-handed antineutrino. The reason is that the Hawking emission doesn't have the helicity suppression that is present in weak interactions. So in principle, this means that if you have some population of primordial black holes in the early universe, you can have a source of light right-handed neutrinos that could have some impact in the evolution of the universe. And this is what we consider in this work here. The other option is that neutrinos are Majorana, as I was saying, you can have that you can not only have the active neutrinos that we are measuring in oscillations, for instance, but you can also have heavy right-handed neutrinos, like those appear in the seesaw mechanism. And in this case, what will happen is that if black holes emit these heavy right-handed neutrinos, they can contribute to the formation or the generation of matter antimatter's asymmetry via the leptogenesis scenario. This has been considered in the literature before, but we have also considered this in this work. And the idea is that you need to include also the thermal production of these heavy right-handed neutrinos. And there are many consequences. And these are the two acts that I will now focus on. I will talk first about the implications in the Dirac case, and then talk about the implications in the purely Majorana case. Okay, so this is the first act. This is basically mainly based basically in this work with Cecilia. And what we assume is that, oh, okay, we know that neutrinos are massive particles. Let's assume the minimal extension of the standard model. In this case, we will add right-handed neutrinos and add Yukawa terms like this. And since this will be the only source of masses of neutrinos, we know that these Yukawas need to be very small, given the value of the vacuum expectation value of the Higgs. So since these Yukawas are very small, what happens is that it has been proven that in this minimal case, these right-handed neutrinos cannot be produced thermally in the early universe. And if you have some source of these right-handed neutrinos, they don't thermalize with the standard model plasma. So what is the idea here? What we will assume is the following. Let's say that for some mechanism, there is an initial density of primordial black holes that form at some initial time and a formation temperature. After some time, because of Hawking radiation, these primordial black holes evaporate. And during this evaporation, they emit these right-handed neutrinos. Interestingly, depending on the initial fraction of these primordial black holes, you could have that they could have dominated the evolution of the universe. So you could have a non-standard cosmology. The reason is that, for instance, black holes basically behave as matter. And if you have, since this basically depends on a to the minus 3, a being the scale factor, if you have an initial small fraction of these primordial black holes, they could have dominated the evolution of the universe. Here, what I'm showing is assuming, for instance, an initial mass of 10 to the 7 gram, and this initial fraction of 10 to the 13 or 10 to the minus 7. So in the case of 10 to the minus 7, as you can see here, this is basically the contribution of radiation, black holes, and right-handed neutrinos, the each contribution to the total. So at some point, black holes dominate the evolution of the universe. And this will depend on this, the initial value of beta prime. And as has been proven before, this value of beta prime, that let's say it's a critical value in which you will have domination, will depend on the mass of the black hole and what I was talking about, this evaporation function. So when the black hole, the initial fraction is bigger than this value, you will have a domination of primordial black holes. But okay, what's the effect? So when the black holes are emitting these right-handed neutrinos, after they evaporate, these right-handed neutrinos stay in the universe since they don't thermalize. And they constitute a contribution to the number of the relativistic numbers of the degrees of freedom. So at, for instance, matter radiation equality, you can put constraints to the density of these right-handed neutrinos because they will contribute to delta N effective. So in general, you can consider what is the impact of having an additional density of right-handed neutrinos coming from the primordial black holes. And this is basically this is the contribution to delta N effective, and will depend not only on the degrees of freedom at the evaporation, but also on the density of the right-handed neutrinos that are emitted. So let me just go back to this plot that I showed you before, and I will zoom in the region where the constraints are weaker. That is when the black holes evaporated before BBN. This is the zoom in. Here you have the constraints of BBN that I was showing before. So as I was saying, if the initial black hole or the initial mass of the black holes is less than about 10 to the 9, these black holes would have evaporated 10 to the 9 grams. These black holes would have evaporated before BBN. There are some constraints here, but these are more model-dependent constraints. For instance, one constraint that one can have is that with if we assume some supersymmetric sector, and if you assume that there is the existence of a stable state like the lightest superpartner, black holes would also emit all the superpartners, and they could lead to the emission of these. So you can have some density of these light superpartners. And since you don't want to overclose the universe because they can constitute dark matter, you can put some constraints here. But again, this model, this constraint depends on the existence of this supersymmetric sector. Other constraints that are less, well, more or less model dependent are this entropy constraint. And other constraint is the so-called Planck relics. These constraints come from the fact that when black holes evaporate and when the mass of the black hole is closer to the Planck mass, we don't know what happens because the semi-classical approximation that Hawking used to derive the radiation breaks down. So in principle, you can assume that black holes totally evaporate, totally disappear, but you can also have that because of some gravity, quantum gravity effects, the evaporation stops down. And any black hole that was evaporating will leave some kind of relic. And this relic will have masses that are a few times the Planck mass. So in principle, these Planck relics could be still around and they could constitute the dark matter. So if the initial density, the initial beta prime is bigger than this value, in principle, you can have that these Planck relics would have overclosed the universe. But again, we don't know what happens with the evaporation when the mass goes to the Planck mass. So this is very model dependent as well. It's quantum gravity realm, so we don't know what happens there. So this is what happens when you assume that the neutrinos are Dirac and they are emitting these right-handed neutrinos. The current constraint is, let's take the value from Planck at the 2 sigma level, and this is the constraint we get. So this region here is excluded, while the region to the left is not excluded. And the reason is that the delta N effective coming from these values, from values to the right, to the left, sorry, are smaller than this value. But again, we can study forecast of considering the sensitivities of future experiments, like the South Pole Telescope at the SMB stage 4, and assuming that they can achieve their expected sensitivities on delta N effective, we observe that we can improve by a lot the constraint in the case of Dirac neutrinos. So in principle, if the South Pole Telescope, yeah, for instance, sorry, there is a little mistake here. This should be the dash line, that these are the dot line. So if the South Pole Telescope achieves this sensitivity, this value on delta N effective, this region would be excluded in the case of Dirac neutrinos. Interestingly, since these black holes are emitting these additional degrees of freedom, in this region of the parameter space, you can have a delta N effective, which is between 0.2 or 0.37. And as has been pointed out, having an additional contribution to delta N effective can alleviate the Hubble tension, but it doesn't solve it by itself. Okay, but since we have these right-handed neutrinos that were emitted, they could still be around us. So one may wonder, is it possible to detect these right-handed neutrinos? So the first thing we can compute is the diffuse neutrino flux from the primordial black holes. And basically is integrating the Hawking rate, assuming, including the redshift, and including the evolution of the universe by including these factors. So let me just show what is the result. So this is more or less the same plot that I begin with. This is a more compact version. So here you have the flux of the neutrinos from the big man, the C nu B. And here you have solar neutrinos, the atmospheric neutrinos, and the diffuse supernova neutrino background, which is the other type of neutrinos. So the different lines correspond to initial masses, different initial masses. So for instance, as you can see here, in the case of an initial black hole, which had a gram, the flux of neutrinos is relatively large. It's higher than the solar contribution. And actually, it's at values which the momentum of the neutrinos is very small. So these neutrinos would be non-relativistic today. And you can see when, for instance, you start to increase the initial black hole mass, at some point, this start to be reduced. And the reason this is reduced is because this depends on the number of degrees of freedom, or the number of black holes, and the number of black holes is inversely proportional to the black hole mass. So this reduction comes from that. So we observe that in principle, you can have a large density, a large flux of these right-handed neutrinos. So one may wonder, is it possible to detect these right-handed neutrinos? So in order to detect these neutrinos, we need to, again, consider weak interactions. Even though these were not created via weak interactions, if we want to detect them right now, the way is using weak interactions. So given that these are right-handed neutrinos, we need to pay the helicity suppression. So in principle, for the case of a black hole with a 1 gram, as we can see here, the helicity suppression is not strong. And the helicity suppression is basically the mass over the energy. And the price, for instance, for a 1 gram black holes is about 10%. So in principle, the price is not that big. But when we consider the specific values to detect these neutrinos, we observe that the value is very small. So what is the type of interaction that we can consider for detecting the neutrinos? It's the same one that I was talking in the beginning to detect the cosmic neutrino background. Is that the capture of a neutrino for a neutron producing an electron. And putting some numbers, if you assume neutrinos as Dirac, as we are assuming here, the cosmic neutrino background have a rate of about 40 events per kilogram year. But when you compute what is the value of the capture rate for these right-handed neutrinos, you have that is about 10 to the minus 2 per kilogram year. So even though even though this flux is relatively large, the cosmic neutrino background is way higher. As you can see here, this is a log scale, so you still have some orders of magnitude compared to the cosmic neutrino background. So the flux is still suppressed, and the difficult thing is that if you want to detect these right-handed neutrinos, first you need to detect the cosmic neutrino background, and this will be a background for your searches of these right-handed neutrinos. So this is something we are still considering if there are other ways to try to detect these right-handed neutrinos. Okay, so I will move now to the second act, and is considering neutrinos as Majorana particles. And this is work done with collaboration with Jessica Turner. So let me just remind you briefly what is leptogenesis. So from the observation in the universe, we know that there is a non-zero asymmetry between matter and antimatter. And observing, for instance, at the CMB or BBN, we observe that it's about 10 to the minus 10. And this eta is basically the ratio between the difference between baryons and active baryons, the densities, over the photon densities. So as you can see here, for basically, these are small numbers. So in order to create this baryon asymmetry, Sakharov pointed out that you can consider create it from a symmetric universe if you have baryon and lepton number violation, if you have CP violation, and if you have temperature from thermal equilibrium. Interestingly, this is not fulfilled in the standard model. So you need some BSM physics in order to create this matter-antimatter asymmetry. So for the case I will focus on, which is leptogenesis, what we will assume is that we will add to the standard model basically right-handed neutrinos, but in this case, what we will consider is they have additional Majorana masses. And because of these Majorana masses, what you see is that you won't have, the neutrinos will be Majorana particles, and thus you will violate the lepton number conservation. So in this case, the first condition from Sakharov is fulfilled in this scenario. And when you put some numbers, for instance, if you want to know what is the value of the masses of these right-handed neutrinos, when you consider what is the masses of the active neutrinos, you observe that if you want Yukawas of order 1, the masses of the right-handed neutrinos should be very high, like order 10 to the 12 GeV. And from the next, this is for the case of a simplified approximated form, but if you want to be more careful, you can relate the neutrino masses, the active neutrino masses, to the right-handed neutrino masses via this parametrization that is called the Casasi-Barra parametrization, and this is the one I will use later on. So this depends on the neutrino selection mixing that we observe, this PM&S matrix, and it depends on also in complex orthogonal matrices. So interestingly, since in this Yukawa matrix can have some phases, you can have sources of CP violation, additional sources of CP violation here. So in principle, if you can have additional CP violation, fulfilling the second condition of Zakharov. The third condition is considered when you analyze the evolution of the universe, and you consider, for instance, Boltzmann equations that will tell you what is the evolution of number densities of these right-handed neutrinos and the number densities of B minus L, that is basically related to the baryon asymmetry. So you can write Boltzmann equations for this, but I prefer just, in order to understand this, let me just put some, the general idea of how this works. So when the temperature of the universe is around the mass of the right-handed neutrinos, these particles are created because of these inverse interactions. Like you can have that a very high energy lepton interacts with the Higgs, and it produces these right-handed neutrinos. And since the universe starts to cool down, these right-handed neutrinos can reach the equilibrium, but after that, they will no longer be in the equilibrium, and they will decay, violating in the, they will decay in a different way for leptons and eigenleptons. So they will create a lepton asymmetry in their decays. And after that, via Faleron process, this lepton asymmetry can be converted into baryon asymmetry. So schematically, if you assume, for instance, the right-handed neutrino mass to be, I don't know, 10 to the 11 GeV, and defining this very crucial parameter, which is basically the ratio between the mass of the right-handed neutrino to the temperature of the universe, we can observe this mechanism at work. So let's assume that you have an initial abundance taken to be 0. And because, again, these inverse interactions, this starts to rise because of the number density starts to be increased. But at some point, this right-handed neutrino abundance reaches the equilibrium. And because of the expansion of the universe, because the expansion of the universe becomes larger than these interaction rates, these particles start to decay. And after that, this blue line here corresponds to the B minus L asymmetry that you create. And when the Z parameter, that is when the temperature of the universe is much smaller than the mass of the right-handed neutrinos, this density, this B minus L asymmetry, freezes out. So in principle, you can have the generation of the baryon asymmetry that we observe of the universe. So before going to the specific case of the primordial black hole effect, let me just do a shameless propaganda about this code that we are calling Ulysses. And the idea of this code is that this code solves these Boltzmann equations for different models of leptogenesis. This model that I'm showing here is the simplest thermal leptogenesis, but you can have other models. And the idea that we put out this code is to put different effects that can impact the final baryon asymmetry. For instance, I didn't speak in the example before, but you can have flavor effects that can play a role. You can have loop effects, spectator effects. You can change, this depends on what is the cosmology that you're assuming, and you can have washout effects. So all these effects are trying to destroy your baryon asymmetry, but at the same time, this asymmetry is driven by the phases. As I was saying, this depends on CP violation, and it depends on your Boltzmann equations. So the idea of our code, that is called Ulysses, is compute leptogenesis via decay and resonant leptogenesis. And we wanted to do it in an easy way that, in principle, anyone who has a model for leptogenesis can plug in their model there. And it's easy to parallelize, and it's rapid. It has a rapid evaluation. and it can perform multidimensional scans of parameter space. So this code is written in Python, and if you're interested, this is the reference for that code. But okay, this is the end of my self-propaganda. Let me move on to understand what is the effect of having primordial black holes in the final asymmetry. So the idea is that I will assume the same as I assume for the Dirac case. Black holes form at some point, they evaporate, and interestingly, in this case, is that since they can have these black holes will emit right-handed neutrinos, they can have an impact, because when these right-handed neutrinos are emitted, this can decay, producing an additional lepton asymmetry. So in order to do that, we wrote down some specific Boltzmann equations. Let me just say quickly what it means. Basically, we have an equation just for the thermal contribution, because we are assuming that the thermal contribution that I was speaking before is present, but you have an additional source coming from the evaporation of the black holes. So in this case, these are the number densities of the different, we are separating the thermal and the black hole emitted. And then we study both contributions, the thermal and the emitted from primordial black holes, to the final baryon asymmetry. And we are including flavor effects. Something very important is that when primordial black holes evaporate, since they are evaporating, producing a lot of particles, they are changing the entropy of the universe, and actually they are increasing the entropy of the universe. And this will have some important, crucial impact on the effect of the final baryon asymmetry. So there are basically three scenarios that we can consider depending on when the primordial black hole evaporated with respect to the thermal scenario. By this, I mean, first, primordial black holes could have evaporated before the right-handed neutrinos are thermally produced. They could have evaporated more or less at the same time, or they could have evaporated after the thermal leptogenesis. So what we observe is that, well, if black holes evaporate before the right-handed neutrinos are thermally produced, this only constitutes an initial condition for thermal leptogenesis, and the effect is not important. So in this case, having these primordial black holes evaporated, they don't change the final asymmetry that you have, and it will be the same as in thermal leptogenesis. More interesting things happen when you start to consider, for instance, that primordial black hole evaporation occurs more or less at the same time that thermal leptogenesis. So let me just show you some examples. For instance, I will assume just a black hole mass of 1.7 gram and an initial flux of 10 to the minus 3. And these dark yellow lines correspond to the thermal leptogenesis that I was showing before. So in this case, we have an additional contribution coming from the black holes. And this, as you can see here, there is a point that it starts to increase very fast. And this happens when we are close to the end of the lifetime of the black hole. Because when the black holes are close to the end of their lives, the evaporation accelerates and it leads to an explosive scenario, explosive stage, sorry. So after that, you reach some value, and the remaining right-handed neutrinos, they decay quickly. So what is the impact here? So the impact on the final baryon asymmetry is that you can have both contributions, the contribution from thermal leptogenesis and the contributions only coming from the primordial black holes. But there is the important effect that I was talking about, since the green line corresponds to when you put the two things together. So in principle, the right-handed neutrino abundance is basically the sum of the two right-handed neutrinos, or the two right-handed neutrino densities. But the total baryon asymmetry is not exactly the sum of these two cases. And the reason is that, as I was talking before, there is an impact of the black hole evaporation here, because black hole evaporation are emitting, let's say directly, a lot of photons that will modify this photon to baryon ratio. So in a sense, what is changing, black holes are contributing not only to the numerator of this ratio, that is to the number densities of the baryon asymmetry, but also to the denominator, because they are emitting a lot of particles, a lot of photons. So in principle, what we are observing here is that black holes are actually diminishing the asymmetry, and it's close to what it would be only in the case that you have the emission of these from purely primordial black hole emitted, the asymmetry. The third case is that when the black holes evaporate after the thermal leptogenesis era, again, let me just change some values here, and these are the values that the same standard number densities that I was showing before. So in this case, since black holes are emitting after the thermal leptogenesis era, as you can see here, this line becomes more or less constant. It means it's constant because black holes are emitting particles, but these particles are also decaying at the same time. So in a sense, this becomes constant because the production rate is equal to the decay rate of these right-handed neutrinos. But at the same time that these right-handed neutrinos are decaying, they are still producing some non-zero baryon asymmetry, as we can observe here. So when we sum, again, this in the case of the right-handed neutrino density is just the sum, but we observe again the depletion here coming from the fact that these black holes are injecting a lot of entropy here. So we can take another value. So this is when Z black hole, which is basically the mass over the temperature of the black hole, is around 1. But what happens if we consider large values of this Z black hole? So in this case, we have like a black hole of 10 to the 4 grams. And in this case, the emission of the right-handed neutrinos is suppressed. And the reason is that as I was talking before, the mass of the black hole is much larger than the temperature of the black hole, and the emission of these particles is Boltzmann suppressed. So the only effect here will be that black holes would only deplete the final asymmetry that we observe here from thermal leptogenesis scenario. So okay, so this is what for different values of the black hole mass. So we can now plot what is the dependence of the baryon to photon ratio as function of the initial black hole mass. Sorry, there should be black hole here. And for a fixed value of the initial density, that let's fix it to 10 to the minus 3. So this dashed line here corresponds to the value of without primordial black holes. And we can separate the different eras that I was talking before. So for instance, when this full line it's equal to the dashed line is when the black holes evaporated before the thermal leptogenesis era. And we see that when black holes evaporate around the thermal leptogenesis era or after, we only see a depletion. There is a little of mitigation around when the Z black hole is around 1. And the reason is that these black holes can, you are in a, let's say, in a sweet spot when the emission of these right-handed neutrinos, it's important, the final baryon asymmetry. But the conclusion here is that black holes are always reducing your baryon asymmetry, even in this case, even basically for all cases. So this was for a fixed value of the right-handed neutrino mass, let's say 10 to the 11 GeV. So what happens if we change the mass of the right-handed neutrinos? We observe that the depletion is always strong, but for the values of the Yukawas that we were considering, this depletion, I mean, you can still play with the values of Yukawa in order to get the observed value of the relic, of the eta B or the matter antimatter asymmetry that is observed, that is this value. So in principle, even though that you can have, we choose some specific values, but you can change the values and you can still have a successful leptogenesis in this scenario of high masses of the right-handed neutrinos. But if your masses of the right-handed neutrinos, for instance, are smaller, which is the case of the intermediate scale leptogenesis, which let's say the masses are between 10 to the 6 and 10 to the 8, first, there is no the mitigation I was talking before. You see only the reduction of the baryon to photon ratio, and for some values, assuming even fine-tuned Yukawas, you see that you find a very strong depletion due to the evaporation of the black holes. So we are assuming these fine-tuned Yukawas because it's the case when you can maximally enhance the emission of right-handed neutrinos, and you can maximally enhance the final baryon asymmetry. So even in those cases that you are fine tuning to have a maximal production of baryon asymmetry, you will see that you can deplete, for instance, in the case of 10 to the 6 GeV, you deplete the baryon asymmetry orders of magnitude. So this means that there is, if you find that the universe had some initial density of primordial black holes with masses of around 10 to the 4, you see that there could be a significant tension between the intermediate scale leptogenesis and the existence of these primordial black holes. So, okay, before I was assuming a fixed value of your initial density. So what happens when you change your initial density? So again, just this color code means with an blue, it's not changing the value in the thermal case, and more red, it's more depletion, and it depends on the case of the masses here. So this line here is if you have an initial density bigger than this value, you will have a primordial black hole dominated era. So as you can see here, when you assume a primordial black hole dominated era, the depletion is always present and can be large in this case of, for instance, 10 to the 8 GeV, because it can reduce the baryon asymmetry and orders of magnitude. And here is about 5 orders of magnitude. So as you can see here, this diminution, it's not depending, it depends on the actual value of beta prime, but the effect is always present. So this diminution is a generic feature that we should take into account. So, well, one may wonder, well, you're assuming that you have some initial density of primordial black holes, and this can have a significant tension with the intermediate scale leptogenesis, but how can we prove that? So in principle, some works have tried to look for the gravitational waves that are produced because these black holes will emit also gravitons, and you can try to detect these gravitons, or others, you can produce gravitational waves in other ways. So some recent works have tried to point out, like, can you look for these gravitational waves? And if so, can you constrain these primordial black holes? And in principle, it seems feasible, not in the near future, but probably in the far future. So in principle, you could try to look for these gravitational waves. So here I'm just showing an example of what happens if with the spectrum of gravitational waves produced directly from the evaporation. You can have other sources of gravitational waves. And the reason that this is difficult is that in this case, in this specific case, these values are for huge frequencies. These are at the terahertz. And right now, this is not very feasible. But in principle, you can have other gravitational waves that can be detected on other detectors, or the other ways to detect these gravitational waves. But the conclusion is that if you look for these gravitational waves, and if you look and you observe that in the universe had some initial density of primordial black holes with some masses, specific, let's say between 10 to the 3 and 10 to the 5 grams, this would put a significant tension in the leptogenesis, in the intermediate leptogenesis scenario. Okay, so to conclude, so the code of my work of this presentation, the first thing I was talking about is that primordial black holes depends on whether neutrinos are Dirac or Majorana particles. If in the Dirac case, the interesting thing is that since you have the additional degrees of freedom, the right-handed neutrino and the left-handed neutrino, these degrees of freedom can be produced from primordial black holes. And because of that, since these will be light particles, they will contribute to the delta N effective. So in principle, you can derive some constraint applicable only for Dirac neutrinos, given the measurement of N effective by Planck. In that case, we observe that the flux of right-handed neutrinos can be large, but with the simplest way to try to detect them is still difficult to see if you can measure these right-handed neutrinos. On the other hand, if neutrinos are Majorana particles, and if you assume, for instance, the type 1 seesaw, in that case, black holes with also emit these heavy right-handed neutrinos. But the main effect that we observed is that black hole evaporation will diminish the baryon asymmetry, because these black holes would emit a lot of particles, And basically, they will emit photons and many other types of radiation that will increase the entropy of the universe. Interestingly, if you prove that existed some primordial black hole density with mass, let's say between 10 to the 3 and 10 to the 5 grams, you can falsify intermediate scale leptogenesis, because in that case, even if you assume very fine-tuned Yukawas, the diminution created by the primordial black hole evaporation wins over this extremely fine-tuned. So one thing we can consider is, well, what about other leptogenesis scenario? What about other models? This is something that we are working on. So just we have that more phenomena is yet to be explored. So thank you very much.
Excellent. Thank you very much, Yuber, for this super nice presentation. Are there questions or comments? So one thing, let me remind you that, that you can ask questions to Yuber via the YouTube chat. So I think that we have one.
Yes, thank you, Yuber, for this very nice and interesting talk. I have a couple of questions. They are probably very naive questions. So one, when you impose constraints on the beta prime or the black hole fraction, at the moment when you are scanning the masses for the primordial black holes, do you consider at that point that given a mass, then all the primordial black holes have the same mass, and then, or there is some mass distribution function over which you weigh your constraints? That is the first. And the second is that these constraints coming from looking at the effects on the number of species that can be evaporated from the black hole. Isn't that just also affected by pretty much any new physics? I mean, it could be that instead of emitting two neutrinos, it emits a neutrino and some very light dark photon and things like that. So similarly, I mean, similar to, you mentioned, for example, the LSP constraint, right? It could be that basically you get the same effect of emitting two neutrinos by emitting a neutrino and something else. After all, the only interaction here that is involved in the production is just gravity, right?
Yes. So regarding your first question, yes, sorry, I forgot to mention that we are assuming that when all black holes form, they all have the same mass. But applying, so in other words, what we have is a monochromatic distribution of primordial black holes. But extending this to some more, let's say, realistic distribution, it's not difficult. It's just considering what is the distribution of these masses. And your second question, yes, in a sense, when we derive this value, we are assuming that you have 3 additional light degrees of freedom. That is the right-handed neutrinos. Well, actually 6, because 3 times neutrinos and tiny neutrino. So in principle, if you have some extended sector that has some, I don't know, number of degrees of freedom, some number of, I don't know, dark radiation, this could be extended to those types of scenarios, yes. So, but it will depend on the specific case, right? Because here you cannot assume, well, you can assume some values or generalize these, but yeah.
Thank you.
Okay, thanks. I can see a question from Enrico Bertuzzo. He's asking, does the LSP bound apply to general dark matter emission, not only in the supersymmetric case?
I believe that this was only compute for the supersymmetric case. For dark matter, because in that case that you have, let's say you assume the MSSM, and you assume some, I don't know, R parity, etc. So it depends on the number of degrees of freedom, because let's say that you have, I don't know, many particles, winos, whatever, that will decay on the lights like the superpartner. So it depends on the specific set of particles that you have in your theory. So for other dark matter models, it will depend on how you write your sector. So this is what I mean. It depends on the number of particles that you assume you have.
Okay, thanks. Are there more questions or comments? Well, about this slide, what happens at 10 to the 9 grams? We have this vertical dashed line?
Oh, this is just, I was just separating like the BBN constraints with the entropy constraints. It's just saying that below here, the BBN, black holes would evaporate before BBN. So you don't have any constraint.
Okay,
It's just
that,
separation between these three regions.
I'm colorblind, but that I think is blue line. You say that correspond to
Oh, sorry.
right?
Yeah, the full line is, yeah, the full line is the, this full line is the Dirac neutrino constraint. These dashed lines are just separating with it. Yes, on delta and effective.
But then why are you stopping at 10 to the 9?
Oh yeah, yeah, I see what you mean. Actually, in the paper we extended here. Here I'm stopping here because it's just extending this line, and I didn't put it because the BBN constraints are much stronger.
Okay,
but
in principle,
you're right.
You could
This line
go
extends.
till CMB.
Yeah, exactly.
I see. Okay, thanks. There's another question by the Basish Bora. He says, if the neutrinos have some extra interactions via which they can thermalize, can we relax the bound on PBH fraction compared to the non-thermal case?
Yeah. I mean, as I was saying here, I'm assuming this minimal extension, and in this case, the black holes don't thermalize. But if you add some other interactions here that can make the right-handed neutrinos thermalite with the plasma, these bounds are relaxed, because basically what it means is that the right-handed neutrinos won't remain in the universe. They will, when they are emitted from the black hole, they will basically thermalize with the plasma. And of course, these constraints that I'm showing here, this stop. Basically, they will change. Yeah, but again, it depends on the assumed interactions, because let's say that you have an additional interactions. I don't know. Let's include that neutrinos have, I don't know, a U1 interaction. Black holes can also emit the specific particles of that interaction, like the additional mediator, or if you have, you need other particles to cancel anomalies, for instance, those will be emitted by the black hole.
Okay, thanks. Further questions or comments to you? I have one. So if I understood correctly, you say that PBH always decreases the asymmetry, right?
Yes. Mm-hmm.
So, and that's because of the entropy injection, right? But what about, what if you take a beta small enough? So maybe you will not dilute, but you will not produce right-handed neutrinos either, right? That's the point?
Yeah, so let me go there to that plot. So here, for instance, it depends on the mass of the right-handed neutrino, right? But as you can see here, if you go below the black hole domination, what happens is that the density of black holes is small, so they don't affect anything. I mean, they produce few particles, few right-handed neutrinos, but they don't affect the thermal value that you get in the plasma. And also the entropy. The entropy, they are not affecting much the entropy of the universe, so they don't affect what is the value of the final baryon asymmetry here. Of course, this is assuming that the thermal contribution is always present. But you can always have that you can somehow, for instance, considering a different reheating temperature, that your thermal contribution wasn't there. So this will change in that case.
Okay. I see another question now from Jorge Diaz. He said, the general claim is that CP violating neutrinos will explain the matter-antimatter asymmetry. What is the theoretical value or range of the CP violating phases that will really answer this question?
So what I was saying is that when you, in just the standard leptogenesis, thermal leptogenesis, there are some phases, additional phases here. For instance, you have a phase coming from the neutrino oscillation mixing. That is the phase I was talking in the beginning. But you can have additional phases when you parameterize in this way. There is no specific range because in principle, you can play with many parameters, because as you can see here, this depends on the mixing angles. This depends on the actual masses of the right-handed neutrinos, and the active neutrinos, and this depends on this complex orthogonal matrix. So in principle, you can play with all these parameters, and there is no one specific range. It needs to not be zero, but since we have many parameters, there is no a specific range.
Okay, thanks.
I have a question which is connected to your question, Nicolas, regarding the dilution of the eta. So this, of course, is mainly related to as both you and Nicolas were saying, to the increase in entropy, right? But so where does a heavy neutrino mass come into play? I think I missed that effect, because at the end of the day, the black holes are decaying after, they're decaying late, right? So so where does a heavy neutrino mass, I mean, what's the role of the heavy neutrino mass there?
Yeah, let me go back. Okay, let me just show you, for instance, there are two effects. The first effect is that when the neutrino is very heavy, the emission of these neutrinos should be, the temperature of the black hole should be bigger than these masses of these neutrinos, right? If they, for instance, let me just focus on this line, of this blue line, that is a value of 10 to the 9. At some point here, there is still some emission of these right-handed neutrinos. So it will depend on what is the actual temperature of the black holes, because if the black holes have a small temperature than temperature smaller than the mass, they won't emit effectively these right-handed neutrinos. So, and in that case, they will only emit radiation, and this only will diminish the asymmetry, as we saw, for instance, in this case. Here, I am assuming a black hole of 10 to the 4 grams. And if I remember correctly, the mass is 10 to the 11 GeV of the right-handed neutrinos. So in this case, these black holes have a mass of, just looking at this Z beta, 100 times smaller than the right-handed neutrino mass. So you don't emit any right-handed neutrinos, but black holes still emit all types of particles, and the only effect here is that you have the suppression, entropy suppression. Yeah, so it depends. There is basically this game between the temperature of the black hole and the right-handed neutrino mass.
I see. Okay. It's not as simple as just okay, great. Thank you.
Thanks. There's another question, sorry, I forgot it, from Steven Weiss. And he's asking about Majorana neutrinos, and he said, will it imply that the mass could be generated by a mechanism in which the neutrinos have gravitational interaction with some particle?
Sorry, that could you repeat? I didn't.
I'm not sure I understand the question, but maybe he's just wondering about the Hawking evaporation, just a purely gravitational mechanism for producing particles. So he said exactly, will it imply that the mass could be generated by a mechanism in which the neutrinos have gravitational interaction with some particle?
In principle, I think, in principle, I think you can have sources of, let me go back here. Additional sources that, for instance, you can couple the right-handed neutrinos with, I don't know, some gravity or some spin to particle. But I think the effect of the Hawking radiation is independent on the generation of mass of neutrinos. The important thing is that as long as you have some specific model, when you have some specific number of degrees of freedom, all these degrees of freedom will be emitted by the black hole. And in that sense, it's closed because you need to know first what is your generation of neutrinos, your mass generation mechanism of neutrinos, or what are the specific degrees of freedom. So in principle, I guess you can have many other terms that can generate masses, like with gravity, but these are two different things. I'm worried more about this semi-classical region where black holes are considered classical objects, well, semi-classical objects, and they emit particles. It's not related to the mass mechanism. I hope I answered the question.
I think so, but Steven, if you want to add something, please go ahead. Otherwise, Oscar, yes, please.
Thanks, Yuber, for your nice presentation. So I have a couple of questions. So at the end, it's possible to have right-handed neutrinos with lower masses than the limited by the Davison Ibarra bound. Is that true?
I believe so, but the problem is in that case, if you want to explain neutrino oscillations, you need additional terms here, right? Like an additional interactions or other particles that can contribute to the masses of the neutrinos. So in principle, you can violate that bound, but it would mean that you would have additional sources of of masses, additional masses.
Okay. So what are your prospects regarding TB leptogenesis models? So do you think that maybe what are your prospects?
Okay, so let me just go back. There is something I wasn't mentioning, and the reason I'm stopping at 10 to the 5 is that these black holes with a mass bigger than 10 to the 5 grams, they would have evaporated after the electroweak phase transition. So sphalers won't be active in that region. But in principle, you can consider other types of leptogenesis that, as I was saying, that that happened before the electroweak phase transition. There is some specific case that we are considering that is the ARS leptogenesis. That is basically oscillation between these right-handed neutrinos that could lead to the emission, to the final leptogenesis. But regarding the parameters of the mass of the black holes, you are restricted by this value of 10 to the 5, because if you produce some leptogenesis after this, there is no, in principle, let's say I'm not 100% sure, how do you convert the lepton to baryon asymmetry? But in principle, yeah, for instance, TV leptogenesis or things can be possible as long as you add a specific setup of particles here and you consider the effects. I hope that I answered the question.
Okay, and just one, yes, and just one last question. So it's possible to apply this framework when you have another source of neutrinos for the case of, for example, asymmetric dark matter. You have an initial source of dark matter particles, so maybe in that case you obtain a different answer as the standard paradigm.
Yes. I think since I think Walter mentioned gravity is universal. So if you have another sources for dark matter together with this generation of leptogenesis, basically you can work with them together. The only thing in my point of view, is that you need to start with some specific setup of particles, because the emission depends on the number of degrees of freedom, as I was talking before. So in a sense, working in an effective field theory here, it's a bit more, let's say, complicated, because an effective field theory it means that some degrees of freedom are very high, right? So have larger masses, so in principle they are not accessible. But since black hole temperature operates in an, let's say, non-standard way, since when black holes shrink, let's say when they start to lose mass, they become heater, you will have an access to these heavier states. So what I mean is just, yes, you can have, for instance, additional sources of dark matter and having leptogenesis at the same time, but you would always, I think it's better to start with some specific set of particles.
Okay, thanks, Yuber.
Mm-hmm.
Okay, maybe now last question is again from a chat from Jorge Diaz. So you say something on the lines of, we can always adjust couplings to get the right baryon asymmetry. Mm-hmm. Isn't too much freedom a downside of the theoretical framework? Can this mode be ruled out?
I think the freedom that you have, let me just look at here. In principle, these Yukawas, there are some sort of freedom. The only freedom that I was saying actually just a few seconds ago is that if you want to relate these Yukawas here to the measurements of the neutrino oscillations, you would not have 100% freedom, because if you want to have Yukawas that give account of the observation of neutrino oscillations, you don't have like absolute freedom. But this parameter space is large still, in which you have you can vary these values of your complex matrix, the masses of the Righthanded neutrinos, and still give account of the observations in neutrino oscillations. Other thing is that, of course, there are some theoretical constraints. For instance, you cannot have Yukawas too large because you will violate, I don't know, perturbativity, for instance. Or if your Yukawas have some specific ways, loop effects can make, you can have problems with loop effects. For instance, you can have that the contribution to the mass from loop effects are larger, and let's say the first one loop correction is larger than the mass. So there are still some theoretical constraints on these values of the Yukawas, but even though you have constraints, the parameter space is still large, and you have a lot of freedom.
Okay, thank you very much, Yuber.
Okay, thank you very much.
Super nice talk. Okay, so let me remind you guys that we'll have a meeting next week, Wednesday. We'll have a webinar about the analysis experiment. So we're also very excited about that. So thank you very much, Yuber, and all the audience for the super nice questions, and see you next week.
Thank you very much. Thank you very much for the opportunity.
Thank you, guys. Bye.